Everyone, welcome to. Oh my god, having to speak with you having was terrifying. Welcome to Space Drafts 110. I'm Noah. I'll be emceeing tonight, and for all the newcomers here, welcome. Space Draft is Tucson's version of Astronomy on Tap, a network of events for sharing astronomy with you, the public, in bars and pubs around the world. How our show works is tonight we will have we'll have one 25-ish minute talk, then a 20-minute intermission, and then trivia after that, astronomy themed trivia. The first talk there will be one trivia question, right, Lucy?
Yeah.
One. Okay. And if you when Lucy asks it, you can raise your hand and try to answer it, and if you get it correct, you will win a free bit of merchandise from our table over there. Which brings me to our merch table, it's a bunch of Space Drafts themed merchandise. Unfortunately, it's cash only, and donations are also greatly appreciated. So, here to talk about when molecular clouds love themselves very much is University of Arizona grad student Lucy Steffes.
Okay, hi everyone, I'm Lucy, and I'm a second-year grad student in the Astronomy PhD program at the University of Arizona, and today I'll be telling you about things that are kind of related to my research, mostly, about how baby stars are made, which happens when molecular clouds love themselves very much. So a quick outline, I'll start by talking about why people like me are interested in this. And then we'll walk through the star formation process, starting with molecular clouds in this part of this diagram that you've potentially seen before, and then moving on to droplets, starless cores, prestellar cores, protostars, stars, and then talking a little bit about the ways that stars contribute to the next generation of stars that come after them. So the motivation, why do I and people in my field want to study how stars form? Well, we first have these more philosophical type questions about how did we get here? And it really starts from the molecular clouds before you even have stars and planets, because those are the raw building blocks that you make those things out of. But we also want to know how unique is our sun and our solar system, and we can figure that out by looking at other systems and the way that they form. When do the chemicals and things that are needed for life start to show up? How does that chemistry happen in a very harsh environment like space? And how does matter get from the very large, diffuse, wispy galactic scales down to the super tiny scales that are needed to form stars? And lastly, the question that I'm most interested in my research is how does the surrounding environment of these nebulae impact the type of stars that form from them? And the way that I do this science is primarily with radio telescopes. So here you can see a few pictures of me at some of the radio telescopes that I use in my research. The main one that I currently use is this one here, the Aero 12-meter radio telescope on Kitt Peak. I'm not currently using it, but I did use it this afternoon. But I've used other telescopes too that are listed here. The things that we do with these telescopes are usually making maps or doing super deep single pointings. With the maps, we can study the velocity structure, so look at these clouds kind of in 3D and understand where the different molecules and chemicals fit together and the ways that the gas moves around in the clouds to make stars. But to do chemistry, we want to do super deep pointings where we stare at a single object for a really, really long time, because then we can see super faint molecules that just barely pop up above the noise, and try to understand how they got there. So the molecular clouds. These, as I said in my first slide, are the parents of stars. So they're born out of this cold depth. But many stars all form from the same gas. These clouds are huge, even though they only make up 0.01% of all of the space. But they're very cold compared to the entirety of space. Though sometimes I will complain about gas being too hot when it's 20 degrees. Um, Compared to most things in space, they're also very dense. Compared to things on Earth, still very, very wispy. And in these clouds, they're full of not just gas, but also a lot of. That's where some of the chemistry really starts to happen, especially on the surfaces of dust grains. And I mentioned that these molecular clouds are like parents, so I figured I'd give a shout out to my own parents. Because molecular clouds, the way that they're like parents is because they provide a relatively quiescent and calm environment for stars to form, especially in comparison to very large galactic scales where things are moving too quickly, where baby stars get ripped apart and never really become baby stars at all. They're they're an environment that nurtures these stars and lets them happen. So moving on, the first structures that we start to actually have that could become stars in the future are called droplets. And in this picture, these two pictures here, I'm showing the 18 total droplets that have been discovered and published in the astronomy literature. They're pretty new and not very highly studied things. But we think they happen when these shocks in these very young clouds start crashing matter together in a way that I describe as a hug. So as the clouds give themselves more and more slightly violent hugs, they build up the droplets and increase the density, and then we get things that I'll talk about in the next few minutes. But these droplets are young and they're super small, and they're like an infant. This is me as a droplet. Unfortunately, my dad didn't droplet me. But one of the things that distinguishes droplets from the next stages of star formation is that they're surrounded entirely by pressure, not by gravity. And in this way, they're very much like babies, where babies need to be fully supported for pretty much everything that they do by their community, whether that be their parents or the other people in their lives, or else they won't survive very well. The next step is a starless core. So this happens as those droplets get more and more very violent and high velocity hugs. They're still dominated by pressure, but they have a little bit of gravity going on. They're starting to evolve, but it's still almost entirely pressure bound, where the gas is held together by pressure. They might collapse to form a star, but it's not quite guaranteed yet. They're still young, they're still kind of diffuse and a lower density than future objects, but they are low temperature, which is why where the chemistry starts to, because you get molecules like carbon monoxide, the things that we try to keep out of basements, and those freeze out, they turn into ices at about 20 Kelvin, the temperatures that I think are a little bit too hot. Because if these starless cores are above 20 Kelvin, then we can't usually see as much of the chemistry that I'm interested in. But some of the chemistry happens in gases, which we need to get carbon monoxide out of the gas and onto the ices in order for some of this chemistry to happen. And then other chemistry, like making things like complex organic molecules, need to happen on the surfaces of dust grains. So this is me as a starless core. I liken starless cores to being about toddlers, where they still definitely need a lot of support. That pressure in the starless cores is like support from your family. But they're starting to develop a little bit of their own personality. They're getting a little bit more complex, just like the chemical complexity of starless cores is starting to increase. But they're still pretty young. Moving on, we have these pre-stellar cores. They're right on the verge of starting to collapse, and gravity is starting to play a bigger role. Some of them might be sloshing, the way that this one is right now. B68 is a big example of a core that's sloshing, kind of like a water balloon. squish it. But other ones might be rotating. But some of the biggest signatures that we see in these prestellar cores are collapse. So these cores are right on the verge of tipping either towards not collapsing and making a star, and collapsing and going to the next stage of star formation. Gravity may start to win. Then on the other side of this is, again, the chemistry. Things are really starting to ramp up here, and it's because of a big reasons. Some of those might be age, temperature, density, the larger scale environment, or even things that are precursors to this, like how much dust was even available in the first place. So the larger scale environment things might be how much radiation, how many high energy photons are coming from nearby stars and things like that are breaking the molecular bonds and undoing all of the chemical reactions that we worked so hard to get. To me, as prestellar core. Here, I'm probably about 7 or 8 years old. And while I still do obviously there's a lot of things that I can do independently, but I can't quite survive without my molecular cloud just yet. Okay, so as promised, a trivia question. My question for you all is, what physical condition primarily holds the gas in droplets and starless cores together? Is it A, gravity, B, pressure, C, turbulence, or D? If somebody raises their hand, I'll call on them, because then you can get a sticker. Ideally, somebody who's not a grad student. Yes. It is pressure. I wish I could say it was love, but it's not. Okay, so as I mentioned with the prestellar cores, as these cores start to collapse, they become protostars. So protostars are collapsing, they're spinning, and as many of us may have seen in like a high school physics book or something way back when, just like those figure skaters in the pictures that you've probably seen where they reach out their arms to slow down their spinning, these protostars may start to form disks to conserve angular momentum so that way they don't just spin like crazy. This is where planets may start to form. And I think people who study exoplanets may love for me to talk more about that, but I'm not going to. Here, the density not only increases, but unlike the previous stages that I talked about, the temperature also increases. So they start to glow in the infrared and produce their own heat. Young protostars may also have jets, like we see in this picture. Where they release not only matter, but also energy. Here's also where you might form binary stars through fragmentation. And I think that protostars are a lot like teenagers. Teenagers may start to think that they're kind of like adults. They can do some things that adults can do, just like protostars can start to glow and start to have their own heat, but they're not quite there. Teenagers also often have a lot of energy that they need to release through sports or through a variety of other things, just like protostars have to release jets. And as teenagers grow, they may start to contribute to society and make some of their own things. Stars form their own planets and take projects. So, I mentioned really early on in the talk that these molecular clouds are forming multiple stars at the same time. So usually molecular clouds have a bunch of starless cores, prestellar cores. But there's also structures within the individual molecular clouds. So here we see one of the clouds that I study. This is the Taurus molecular cloud. And here you can see a few protostars that are glowing. So if we go to some figures that I made a few weeks ago, in these families, these are a few smaller clumps of gas within the bigger molecular cloud. And inside of these clumps, we have these cores. So some of them are starless and prestellar, but these ones are protostellar, so they can evolve at different rates within the same small clumps and within these structures called filaments. And I think these filaments are very similar to families. So they have a lot of similarities between the chemistry that's going on within these structures, but they can other rates that they evolve at can be different. So they can have different masses, densities, temperatures, and even some different ages. So I've talked a little bit about families. Also, as I mentioned, this is some of my own research. But here is my family, my siblings. And I think we're most similar to this clump of gas. If you're interested, this one is called B218. Great name. So there's me, I'm the oldest. So because I'm the oldest, and in theory, at least when we were younger, most evolved, this was me, the protostar in the middle. Then my sister here. So this core on the bottom is actually rotating. It's a prestellar core, but it's a little bit more evolved, so it is actually starting to spin. The core on top is not quite spinning yet, but it still is a prestellar or a starless core, so that's like my younger brother. And finally, we get to stars. So stars are actually finally at that stage where they're dense enough and they're hot enough, where in their cores they start to do hydrogen fusion. Bang together two hydrogen atoms and make a helium. And this is called the stellar main sequence. So once those stars actually do form, they may decouple themselves from the molecular cloud that they formed. So this means that they're kind of off on their own, doing their own thing. But once they start radiating, like for real, not like protostars, they contribute to the environment that they grew up in through feedback that sometimes can increase the temperatures, slow the star formation right around them, and change the cloud in varieties. So now we're at the adult stage. For me, I did actually decouple from my molecular cloud. About a year ago, I moved from which I think is definitely moving away from the molecular cloud that I grew up in. But there's also so many ways that we as adults, whether it be the molecular cloud that we grew up in, or whatever cloud or environment we're a part of now. So finally, we reach the last few slides of my talk, where we talk about what happens after stars. Because in the first slide that I had, I showed this figure where we have these circles, where we want to know about what happens to stars at the end of their main sequence life when they've burned through all of the hydrogen in their cores and they need a different way to sustain themselves. So I mostly am talking about these low mass stars. So we're on the left circle. But here they move off of the main sequence and turn into red giants, and they burn through helium and other metals. Sorry, non-astronomers, metals are carbon and oxygen and things like that. But then eventually they shed those outer layers into a planetary nebula. But this enriched gas doesn't just go away. It eventually returns to the interstellar medium and goes back into molecular clouds, where it assists with future star formation. Those products of previous stars we see all throughout our lives, all throughout our solar system, in everything that is bigger and heavier than hydrogen or helium. So here's a few pictures of some really pretty planetary nebulae. And all of this glowing gas around the central tiny little star in the middle is all that enriched gas, the metals, as astronomers call them, that will eventually go back and make molecules with other things in new molecular clouds. So, what can we learn from this whole star formation process? Well, the ways that stars form and evolve apparently mirrors the way that people grow and change. We're also a part of processes that are much bigger than our individual efforts, just like stars are part of bigger communities within their molecular clouds. And as we learned from planetary nebulae, the things will never really be gone after their main sequence has ended. As we learned from the molecular clouds and the starless cores, the droplets, and the prestellar cores, our families, our molecular clouds, our friends, the environments around us are huge supporters of our lives, and that growth and evolution can happen at a variety of rates, and it should happen at a variety of rates. So the last thing that I'll leave you with is, regardless of what field you're talking in, rating your mom's Facebook page can be super productive. Okay, that's all I've got. I can take it.
Are there any questions for Lucy?
Yeah, back there.
What's the time frame from droplet to star?
So it's much.
Could you repeat the question?
Oh, yes. So the question was, what is the typical time frame from droplets to getting to stars? So it's much shorter than the actual main sequence lifetime of stars. So the amount of time that they spend as like your regular stars burning hydrogen. But too short for us to observe. So I think about 1 million to a few million years. So short on astronomy timescales. Meredith, yeah.
What stage is the point of no return? Like at what point do you cross the threshold and we're gonna start collapsing? So like when it
Yeah, so the question was, what is the point of no return? Where once you're collapsing or once you're at this state, you're gonna form into a star. And I think so we'll go back a little bit. So it kind of depends on a few things. So we have the protostars, and those ones have collapsed and are continuing to collapse. But there it depends kind of on mass. So if things are too small to get dense enough and hot enough in their cores, then they don't get hot enough to start doing hydrogen fusion, and you end up with a brown dwarf. But in the prestellar cores, that's kind of where the point of no return can at least start. Because before we get to the prestellar cores, one big interaction with something else can just break everything. So we need it to first be gravitationally bound, like we have in the prestellar cores, especially once it's starting to collapse. But even then, before things are too dense, I think they can still break apart. Yes.
At the very earliest stages, with small disturbances like gravitational waves have any effect?
I don't think so, because I think gravitational waves would be much bigger, but I've never considered that before, so we can talk about that more during the intermission too, if you'd like. Yeah.
Why are those so droplets that have been detected?
Yeah, so the question was, why are there so few droplets that have been detected and studied? One part is that the whole idea of these droplets are a kind of new thing, and they're kind of tricky to find in the first place because you need big, wide-scale maps in specific trace the right kind. So these maps were done using ammonia. So ammonia traces densities of environments that are kind of like intermediate to high-ish. There's gases that survive and exist in higher density environments, but ammonia is a pretty good tracer of getting pretty wide range. But what you have to do to even start to find these droplets is figure out exactly where you're at that threshold of being turbulent and not turbulent. So applying masking and things like that to your data to start to figure out where that happens, but then also having enough of these maps that are wide scale enough, because these things being so diffuse and relatively low mass end up having a pretty big area.
All right, let's see again. Forget who won the trivia, but whoever did comes to us at the bridge table during the intermission. And we will have staff over at the bridge table to interested, and back in 20 minutes, which is, let's call it 8:25. So refresh your drinks and don't forget to tip your bartender. Oh. 8:15.